So far in this course, we've looked at motion in two lenses, okay? Through this lens of kinematics and this lens of forces. And for the next 2 weeks, we're going to be learning a new lens, and that lens is energy. And in my personal opinion, my humble physics teacher opinion, I believe that energy is the most powerful and the most elegant lens with which to explore physics in general and motion specifically, which is what we're focusing on this semester. And part of the reason why I love looking at energy so much is because there's this conservation principle, right? And you guys have probably heard this before where you've heard that energy can neither be created nor destroyed. It can just change forms from one type to another, right? And that allows this like really simple, really beautiful bookkeeping in the universe, right? Where we know that whatever process happens, energy is just moving from one place to another. It's not going anywhere. And if you can just keep track of where that energy is moving, right, or how it's changing forms, then you could solve basically everything that you want to know about the entire universe. And that feels very powerful to me, okay? So I'll start this week with the quote of the week, and it's based on this book by a fellow named Don Miguel Ruiz, and he has a book called The Four Agreements where he says, any well-lived life comes down to really four things: being impeccable with your word, not taking anything too personally, not making assumptions, and always doing your best, okay? And he just dives in these four little kind of truths about a well-lived life in his book, The Four Agreements, and I recommend that if these resonate with you in some level, to go check that book out, okay? I want to then go to the why do we care slide. And there's many, many reasons to care about energy, but one is one of the greatest living examples of conservation of energy happens in our bodies, in our bones, right? Our bones are designed to be a little bit elastic, right? And that elastic quality absorbs energy when we have falls. That like kind of flexibility goes away a little bit as we get older. That's why as folks get old, it's a little bit easier to break bones. Why, you know, when you fall, it can be a lot more dangerous. But I am going to propose this problem that if a youngin is playing in a tree and falls from a height of about 4 meters and lands on his feet, by how much does that femur and tibia compress, right, in order to absorb the energy of that fall? And at the end of this lesson, you will be able to solve that problem, which is kind of exciting. All right. Any chapter on energy needs to begin with the question of what is energy, right? It's not an easy question. In fact, this might be the hardest physical quality or quantity to define. And there's many, many definitions or ways to think about it. The classic textbook definition is that energy is the ability of an object to do work, okay? And it's not work as in the work I'm doing right now that I just showed up to school to make this video. Work in physics has a very specific definition, which you'll find out this week. This is one of the focuses of this week, is exploring this question of what is work from a physics perspective, okay? And that definition works and it's helpful, but I think it's much, much more helpful to think of energy as the currency of the universe, okay? And what do I mean by that? So if you guys can turn to the slide that says the money analogy, you can think of energy as a kind of physics currency. How so? Okay, so I'm gonna make some arguments here. One, energy, like money, can be used to make things happen in the physical world. So for example, one can use money to buy a ticket from New York to Paris, just like you could use chemical energy in a tank of gas in a plane to get from New York to Paris, okay? Two, energy, like money, has different types, right? Different forms of currency that can be exchanged for each other. So just like you can trade $5 for 100 pesos, let's say, you can exchange 5 joules of potential energy for 5 joules of kinetic energy, right? So there's this constantly changing forms, right? And three, the total amount of energy exchange must be constant. This is this principle of conservation of energy, right? So just like when you exchange money, right? If I take $20 out of an ATM in Baja California, it better give me $20 worth of pesos, right? So there's this kind of, just like there's this conservation property with money in a currency, there's also a conservation property with energy. Okay, but the biggest thing that I want to focus on is that energy is the thing that's traded and moved around to get things done in the universe. Okay, and we're going to see many, many examples of how that works. If you guys could go to the next slide that says the incredible variety of energy currencies. So I just want you to take a minute to appreciate all the different kinds of energies that are available for the universe to use. Okay, I want to be clear. These aren't the only types of energy, right? But this is the variety, the largest variety of the ones that we're going to be using in this course. Okay, so I'm going to give you guys about 5 seconds. Pause the video if you want to take a look at these pictures and see if you can decide what form of energy each of those pictures is referring to. And then we will go over them. So starting with the lady running, okay? There's like the little green line zipping past. So this is the energy of motion. What kind of energy is the energy of motion? Kinetic energy, okay? And the next one over to the right of her, there is a caveman who has looking up at a boulder. The boulder is about to fall on his head. Any ideas? That would be potential energy, and specifically gravitational potential energy. So the energy stored in a massive body at a certain height. And you could turn that energy into kinetic energy if it were to fall. Okay. To the right of that are two batteries. This is chemical energy. Okay. There's energy stored in the materials that make up that battery. Then if you look at the atomic bomb, that is nuclear energy. This is the energy that's stored inside of the nucleus of an atom, the energy that's the result of the strong nuclear force. To the right of that is a extremely hot sun, and that would be thermal energy. To the right of that, you see someone pulling a slingshot. This would be elastic potential energy. Remember, potential energy is any energy that's stored. So if I'm pulling back a rubber band, I'm storing energy inside of that rubber band, basically inside the molecular connections inside that rubber, right? And such that when I release it, it can go from that stored energy to the energy of motion, which is kinetic energy. And lastly is that Pink Floyd slide, which is Dark Side of the Moon, okay? And that would represent electromagnetic energy, or the energy that's stored inside of photons. All right. I would like to end this little video by reprising this law of conservation of energy, okay? And I'm going to harp on this a lot because I think it is the most powerful principle in physics, right? It is the least amount of words that you can get the most amount of impact from in all of physics, right? There's so much that we can learn about the universe and so much that we can solve simply by knowing this one principle, which is that the energy of any system, any closed system, stays constant. It cannot disappear, it cannot be destroyed, it cannot be created, but it can change from one form to another, right? So the energy in this universe is always shifting from one form to another, from usable forms of energy to not so usable forms of energy. Keep this in mind because we will use this simple fact to solve a lot of complex problems. When we get back in the next video, I'm going to begin discussing the first energy that we're going to look at, which is kinetic energy. Okay? It's the most simple and it's the most related to the motion work that we've already done. I'll see you there.